let's explore the collision model using the reaction of nitrogen dioxide with carbon monoxide to form nitric oxide and carbon dioxide. And you'll see that below here I have drawn out the Lewis structures of these molecules. So this is just showing their bonding and sort of how they might look geometrically. And these dashed bonds are deliberate, and you don't really need to worry about that too much for this video. So let's say that we can actually watch molecules in motion. We can see exactly what they are doing. And so let's say we have an NO2 molecule here and a carbon monoxide molecule here. And the carbon monoxide molecule is moving to the right, and the nitrogen dioxide is moving to the left. So if this is the case, there is going to be no reaction. And the reason for this is the first part of our collision model, which says that molecules must collide to react. If there is no collision, there will be no reaction. So let's move on to our next set of reacting pairs. I'm going to uncover them now. And so, as you can see, we have 4 pairs of these two molecules, or 2 reactants, and I've drawn them in different configurations. So sometimes the nitrogen is to the right, sometimes it's up, sometimes it's to the left, and then sometimes we have our carbon first, and then other times we have our oxygen first. So we have 4 pairs of reactions. And so one other thing to just note, here I realize that the arrows are pointing directly at each other. Here they're not, but that is deliberate. I want to show the carbon actually going towards this oxygen going towards this oxygen, as opposed to like the nitrogen hitting the carbon here. So if we were to observe these molecules react, which we can do, that is within our powers, in this first pair we would see no reaction occur. And then in the second pair, right here, we would see a reaction occur. In the third pair, we would see no reaction occur. And finally, in the fourth pair, we would see a reaction occur. So what is the difference between these 4 sets of reaction pairs? The difference is their orientation. Just as a sort of side note, I have not drawn every single orientation or configuration of these 2 molecules hitting each other that's possible. I've only drawn 4 just to sort of exemplify the next part of the collision model, which says that molecules must have the proper orientation to react. So that brings us to our third part of our collision model, and I'm going to uncover our last set of reaction conditions. So as you can see here, we have these 3 collisions between the pairs of molecules, our reactants, are actually identical. Well, they look identical, but we'll explore the difference between them now. So let's say we watch the first pair of molecules react and we see no reaction. And then we watch the second pair react and we do see a reaction. And then finally, we watch the third pair react and we see no reaction. So the reason for this is that the first and third collisions, or reactions, they don't have the correct amount of energy in order for the reaction to proceed forward, like I've drawn like this. Whereas the second one does have enough energy for our reaction to proceed forward. And this brings us to the third part of our collision model, which says that molecules must have enough energy to react. Now this energy that we're talking about is the kinetic energy of the molecules. So molecules are in constant motion, and kinetic energy is that energy of motion. And so the amount of energy that is needed for a reaction to occur, like it happens in the second line here, that's called the activation energy. Again, the activation energy is the minimum amount of kinetic energy that these 2 colliding molecules need to have in order for our reaction to happen. So here, down below, I have sketched out a Maxwell-Boltzmann distribution. And so what this Maxwell-Boltzmann distribution is a graph. And in this case, it's a graph that compares the energy, the kinetic energy of collisions, to the number of collisions with that given energy. So if we look over here, the lower energy side, there are just a few collisions that have low energy. And in this middle region here, there are quite a few collisions that have a moderate amount of energy. And then as we go to higher energy, there are fewer and fewer collisions that have that amount of energy. So I can actually draw in our activation energy. Let's say the activation energy is right here. So I'm going to label that. So again, this is the baseline or minimum amount of energy that a collision between these 2 molecules must have in order for the reaction to proceed forward to the products. Now again, I said it's the minimum amount because we could technically have more energy than that and the reaction would still proceed. So any amount of energy that is greater than or equal to this activation energy will allow our reaction to proceed forward, assuming that the molecules have proper orientation and that they collide. Now, of course, this does not actually hold true once we're out at very extreme temperatures, like the surface of the sun or the inside of the sun, because there funny things happen, and we're not really concerned about that. On Earth, like this is the energies that are greater than this activation energy are sufficient for this reaction to occur. So again, in order for a reaction to happen, all three of these conditions have to be satisfied. This is our collision model that explains how chemical reactions occur.